So this is the fourth lecture in the series, and we're going to talk about radio waves. A radio wave is an example of an electromagnetic wave. And electromagnetic waves are generated whenever charge is moved. So yes, you're right. All of the AC circuits we have been talking about will in fact generate electromagnetic waves. In the case of the 60 hertz in your line supply in the house, the wavelength is so long that the power loss is negligible, but it's certainly not negligible over very long transmission lines. And indeed, every place where charges are moved will generate an electromagnetic disturbance. So let's look at the simplest type of electromagnetic disturbance. This is one in which charge is moved up and down along this vertical axis here to generate a time-varying electric field. So as the charge is moved up and down, this field, maximum when the charge is displaced by the maximum amount here, minimum when it's down back at the origin, will propagate forward at the speed of light. That is 10 to the 8 meters per second. It turns out that it's impossible to set up this electric time varying machine without a corresponding and much weaker magnetic field perpendicular to it. And this is why, so it now lies along this orthogonal axis here. The generation of the magnetic field was explained beautifully by Einstein's special theory of relativity. But the bottom line is that one gets a wave that propagates in a direction here that is perpendicular to the direction of charge oscillation and consists of an electric component that lies in the plane of the charge oscillation, shown by this arrow here, and that's called the direction of electric polarization, and then a magnetic field that lies perpendicular to the time-varying electric field. The distance over which this repeats is just given by the time, which is 1 over the frequency of this oscillation times the speed of light, and that defines a wavelength, lambda. So from the argument I've just given, you can see that the speed is the product of the frequency and the wavelength. And so this, of course, is the speed of light for an electromagnetic wave. Now, your power sockets don't generate much radiation, but if the conductor is just the right length for a given wavelength of electromagnetic radiation, then the maximum amount of power is transferred into this radiation field. And that, of course, is the object of radio communications. So we talked about the AC voltages in your main sockets in the house. Where are radio waves? Well, radio waves are much higher in frequency. They typically start at least thousands of hertz and go on up all the way to actually gigahertz and more than that, even terahertz. And the corresponding wavelengths then go from kilometers all the way through to millimeter wavelengths. The wonderful discovery of electromagnetic waves, discovered theoretically by James Clerk Maxwell and experimentally by Heinrich Hertz, is that they unify an enormous amount of physics. Because as you go up in frequency and down in wavelength, you go from microwaves to optical radiation, first infrared and then visible light, then ultraviolet, finally X-rays, and then when the electromagnetic waves are energetic enough, gamma radiation. And what Maxwell showed mathematically was that these were all waves in which a time-varying electric field was accompanied by a time-varying magnetic field, which propagated at the speed of light. And the remarkable thing about Maxwell's discovery was that in his theory, the speed of light was a very simple universal constant. And that's what Einstein took in developing his special theory of relativity. So even although Maxwell predated Einstein by many years, he got it right. So radio waves are part of the electromagnetic spectrum. Let's turn those frequencies into things that are practical for ham radio. This is a chart that you can download from the American Radio Relay League, and it shows the various bands available to radio hams. There are actually bands down at wavelengths of 2 kilometers or 100 kilohertz or so. The most popular low frequency band, though, is 160 meters or 1.8 megahertz. These are all bands which are really pretty local communication, except under unusual conditions at night, where sometimes these waves can be reflected for very long distances. Going a little higher in frequencies, we reach 80 meters or about 3.5 megahertz. And you can see this allowed band covers quite a wide range of frequencies. The different colors correspond to the different parts of the band that are available to the various classes of licenses. And these bits in red here are reserved for Morse code users. So if you tune down to the bottom of this band, you will hear the lovely sounds of Morse code. These are some special frequencies available on a newly made band. Here we go to 40 meters, 7 megahertz, and quite a popular band, gives long-range communication at many times of the day. 30 meters is quite limited, that's 10 megahertz. 20 meters is the favorite band. It's very often open for worldwide communication. 17 meters, fairly infrequently used. 15 meters a bit more frequently used, that's 21 megahertz. 12 meters, 24 megahertz, gives a long-range communication during the day in the right conditions. And then 10 meters, which is beginning to be very high frequency, it's 28 megahertz. That was the band that I referred to in my first lecture, where with my tiny 2-watt transmitter, I worked all the way across the Pacific on Morse code. So when conditions are good, one gets very long-range propagation there. And then here are the VHF bands, 6 meters, which is not all that different from 10 meters. So there are some occasional openings on 6 meters that allow worldwide communication. But generally, when conditions are poor, it's just line of sight. 2 meters, which is almost essentially always line of sight. 220 megahertz, well, that's even more true. 70 centimeters, which is sort of used as a local handheld chat band, and so on up to some of the higher frequency bands. So they all have their own unique characteristics. Where does this come from? It comes from the fact that the Earth is shrouded in a protective shield of plasma, that is ions, separated charges. The separated charges are generated by energetic radiation from the sun. And indeed, it is the formation of these separated charges that protects us here on the Earth from damaging high energy solar radiation. Now, a plasma has an interesting property. The plasma itself can oscillate. That is, the electrons that have been stripped away from the atomic cores of the gases in the atmosphere, separated from them to leave a positively charged ion, can be made to oscillate with the restoring force of the attraction between the negatively charged electrons and the positively charged ions. So they have a resonant frequency. So if you pass a radio wave up into the sky and it lies below this resonant frequency, it will very rapidly be absorbed. If you shoot a radio wave up into the sky that has a frequency much higher than this resonant frequency, the ions simply won't respond and your radio wave will pass straight through. If, however, you shoot a radio wave in at about the resonant frequency, it will be strongly refracted and bent back down to Earth again, and that's where long-range communication comes from. Where is this difference between day and night? Well, in the daytime, the ionizing solar radiation is much stronger, and it forms layers at lower heights, the D layer at about 60 kilometers, the E layer at about 120 kilometers, and then there is a layer that survives the nighttime called the F layer at about 180 kilometers. Clearly, the F layer is going to give you longer range communication than the D layer. Here is a slide illustrating the dependence of the reflection on the frequency of the radio wave. So for radio waves below the plasma frequency of the particular layer that is being met by the radio waves, so at night it would be the F layer, at day it could be the D, E, or F layers. If it lies below the plasma frequency, then it will just be absorbed. That's the blue line. If it lies close to the plasma frequency, it'll be refracted. That's the red line coming down to Earth again, bouncing off the Earth and back up into the ionosphere again. And if it lies at a high enough frequency, it will pass through the ionosphere. So from the bands I was just discussing, you can see that my 30 megahertz long-range communication across the Atlantic corresponded to conditions in which the atmosphere was quite strongly ionized. So instead of passing straight up, my 30 megahertz signal was bounced down to the ground, back up again, and so on around the Earth. The simplest form of communication is just line of sight propagation, which means that the receiver can see the transmitter, and so nothing exotic happens. At least that's what I used to think, but this is very typical of VHF. So, 144 megahertz for 30 megahertz and higher. However, Joe Taylor, K1JT, who won the Nobel Prize for physics for very weak signal techniques that allowed him to discover the effects of gravitational radiation on pulsars, once he won his Nobel Prize, decided it was time to quit doing physics and do ham radio. And he developed a software suite that lets you recover incredibly weak signals. And so the fact that VHF is line of sight is just fine if the moon is in your sight. And so this is Earth, Moon, Earth, or moon bounce communication. And I'll talk about that a little later. A mode of propagation that happens for 30 megahertz and higher is when the E layer, which is the layer just below the F layer, becomes sporadically strongly ionized. And then this can result in what's called sporadic E propagation. And a signal can go a very long way. Typically, if there's enough sporadic E around to give you multiple hops, and one can communicate almost all around the world in sporadic E. F layer is, of course, the most efficient and operates both day and night. And very typically, the 14 megahertz signals in the 20-meter band are bounced off the F layer. And that's why the F layer gives the most reliable long-distance communication. So one is most likely to work the most number of countries on the 14 megahertz band, with the proviso that because everybody's there, it's very crowded, and the guys with the huge signals will get there first, which makes it somewhat frustrating. And it means, therefore, that bands like 28 megahertz are actually quite exciting, because when they open up, you've got no one else messing around, and you can chat as though the person you're talking to is in your living room, and they might be in Tonga or Korea or Timbuktu. So those are all unexpected and exciting things on what makes ham radio fun. Another fun thing to do is to scatter signals of meteors. It was realized by Joe Taylor that meteors, micrometeors, are occurring all the time. Now, it used to be that people would communicate via meteor showers by timing their transmissions to the well-known popular meteor showers, Leonids and so on, Perseids, and then send very fast Morse code repetitively so that when a meteor passed by, a reflection would be heard by a distant station who would then try and reply by the same mechanism. However, a wonderful software, rather like JT65, called FSK41, has been developed to automate these very rapid communications. And so now Meteor Scatter is available essentially all the time because this software is so efficient that even the tiny meteorites that are not associated with big meteor showers are effective for communication. Tropospheric ducting's another mechanism and can result in communication on the VHF bands of hundreds of kilometers. And it occurs when there is a temperature inversion, so that a warm layer of air is trapped above a cold layer and then underneath another cold layer of air. And the difference in air density between the layers of air allows for some reflection of radio waves. And then since this warm air layer can lie there over a distance of many hundreds of kilometers, it can act like a waveguide for the signal. So one can get some extraordinarily strong VHF signals over extraordinarily unexpected distances from time to time. When there are many paths for a radio wave to get from A to B, they're waves, and that means they have a phase, and that means they can interfere. So if one path at a particular time is giving you a maximum in the electric field, and another path is giving you the opposite maximum of the electric field, the net electric field at your receiver will be zero, and the signal will go to zero. So multipath propagation results in, or can result in, this phenomenon of fading. It's shown here for a cell tower and a cell phone receiver, but it applies to any radio communication. So let me end up with another exotic form of communication, one that I have had the pleasure of using in my days when I lived in the United Kingdom. For latitudes that are north enough, lying, north of latitude 45, one gets a line of sight to the beautiful ionization that occurs at night owing to the aurora borealis. So you see a picture on the left of the aurora. And so one can bounce radio waves off the aurora. Now, in the case of the aurora, the gas is moving around so violently that it Doppler shifts the signal randomly. And the result is the nice crisp Morse code that you heard at the beginning of my lectures gets distorted into a raspy hiss. But I do remember the excitement when I first operated during an auroral opening and from the north of England, and heard stations piling in from all over Europe with a raspy hiss. So here I'm going to play a little video of an auroral contact, and you'll hear the quality of the Morse code, or maybe you won't hear it, but that's actually the point. So let's play it. So I hope you just heard that. And if you didn't hear it, maybe it says something about just how rough auroral propagation is. But it certainly is an exciting mode. All right, so we're about done. Next up, antennas and transmission lines.